Hi all, Audrey here. So today we're going to learn an algorithm called the Simplex algorithm. But in order to do that, we're going to start off by doing just a brief review of graphical optimization. The reason for this being that the Simplex algorithm tries to mimic the methods that are used for graphical optimization, but in higher dimensions than 2 dimensions, where we would be unable to really graph the region in question. So we're just going to do this brief review really quickly. We want to maximize c equals negative 2x plus 3y subject to these constraints right here. So this right here, this negative 2x plus 3y is what's called the objective function. And these right here, these are what are called my constraints. Now, the x greater than or equal to 0 and the y greater than or equal to 0, these are what's called positivity constraints. So basically, they're just telling me that I really only care about things where both x and y are greater than or equal to 0. So in order to do this problem, what you guys learned back in high school is that you can actually graph the region of the constraints to figure out the x and y values that satisfy each of those inequalities. So I'm just going to do that really quickly. Okay, so I just graphed the region really quickly. You're not going to have to do this for the simplex algorithm, so don't worry about where this came from. I just thought of each of the inequalities as lines and then graphed those lines. And then this region that satisfies each of the inequalities is this region right here in this particular case. And we call this region the feasibility region. So this is the feasibility region. And what the feasibility region is it's a set of points, feasibility, of points, x and y, such that every single one of those inequalities is true. So what this means is, including the border, everything in that region in there, if I plug it into those inequalities, it will make sense. I will get some things that are less than or equal to 6, and then less than or equal to 12, and then less than or equal to 6, and then less than or equal to 8. All of those inequalities will remain true. So what that means is I want to find the maximum value of c given these points x and y. So which combination of x and y would give me the biggest c? Well, if I look at this objective function here, my c is equal to negative 2x plus 3y, I can actually see that this is just the equation of a line. And if you look, you can kind of see that this is actually the general equation of the line. Well, I'm going to rewrite this line in slope-intercept form. So in other words, 3y would be equal to 2x plus c. So y is equal to 2/3 x plus c over 2. So not only is this a line, from this form, I can see that this is a line, and by over 2, I mean 3 there. Sorry about that, c over 3. Oops. Over 3. So I can see that this is a line with slope equals to 2/3 and y-intercept of c over 3. So with that in mind, we're going to see what values of c would look like over here. So for different values of c, I can kind of think of this as like a line that's floating in space. So it has slope 2/3. Slope 2/3 looks about like that. And so some value of c would give me this line right here. But as that c gets bigger and bigger and bigger, I can kind of think of this line as if it's floating upwards. C getting bigger would just cause the y-intercept of the line to get bigger and would therefore just be floating upwards. So it's like floating up. So as c gets bigger, that line moves upwards. But you'll notice that the first place that it hits when it enters into this region is that corner point 4, 0. So the minimum value, just looking at this graph, we would expect to be that 4, 0. But then as this line keeps floating up, what's the last point that it's going to hit on the way out of this region? That last point will also be a corner point. And that last point is going to be the maximum value of c that can be satisfied by x and y values inside of this region. So in other words, what we're saying is, both the maximum and minimum value of my objective function are going to occur at corner points of the feasibility region. Okay, and so if the maximum and minimum are occurring at corner points of this region, then all we really need to do to figure out where the maximum and minimum is, we don't have to draw the region and kind of like look at that line floating out. We can just check the value of C at each of the corner points. So in other words, we can make a little chart down here where we're like, what's the value of, what are my corner points? And what is the value of C equals to negative 2x plus 3y at those corner points? So graphing this region, I can easily see that my corner points, I'm going to start at 0, 0, and then as I cycle through my corner points, I'll have then 0, 6, 2, 8, 6, 8, 6, 6, and 4, 0. So these are the corner points of this region. Now, if I just plug these things into my C function, I'll know what value C takes at those things. So I'll get 0, 18, 20, 12, 6, negative 8. And what I can see here is that the maximum C value that occurs is at 2, 8, and the minimum C value that occurs is at 4, 0. So if we go back up here and look at this line that was sort of like floating through the region, we did indeed see that the first place it was going to hit with a slope like that was 4, 0. And notice the last place that it hit on its way out would have been that 2, 8. So it makes sense that that 2, 8 is the maximum. So in other words, we can say that this right here is the maximum for C. And this right here is the minimum for C. Okay. So this is just kind of a review of graphical optimization, and what's important about it, what we need to take away from it, is that those maximum and minimum values occur at corner points. So to find the max or the min, we really just kind of have to cycle through the corner points. So how can the Simplex algorithm give us a way to do this, but in higher dimensions? So here, each of these would have just been lines, they just had x and y. What if I also had a z? What if I also had an x4 or an x5? So this method would no longer be reasonable because I can no longer graph that region. So let's take a look at what's called the Simplex Maximization program. Okay, so the Simplex Maximization program is a way of using matrices to cycle through corner points and find the C value at each of those corner points. It can only be used if two very specific things are true. So the first is that x1, x2 to xn are all non-negative, so they're all greater than or equal to 0. And the second is our constraints have to take on a very specific form. We need to have a1, x1 plus a2, x2 plus a n, xn less than or equal to b. So it has to be of the form less than or equal there, and then that b has to be greater than or equal to 0. Okay, so the best way to understand this algorithm is to do a problem and just kind of create the steps along the way. So let's do a problem. All right, so we've got our problem. We have our objective function, and we have our constraints. And like I said, we want to use a matrix to cycle through the corner points. But when we've used matrices before, when we've used augmented matrices, we haven't had inequalities, we've had equalities. So the first thing that we're going to do, our step one, is going to be to introduce something called slack variables. And slack variables are going to turn these inequalities into equalities. So introduce slack variables. Slack variables to turn inequalities into equalities. So basically what we're doing is we're saying that in negative 3x1 plus 8x2 minus 4x3 less than or equal to 40. So there's some x1, x2, x3 that will cause this to either be equal to 40 or to be less than 40. So a slack variable is some number that we're adding that makes up the slack between how much less than 40 it is. So for example, if it equaled to 38, the slack variable would be 2 and make the thing equal to 40. So when I rewrite this with my slack variables, I'll have negative 3x1 plus 8x2 minus 4x3 plus, we'll call this S1, is equal to 40. And so that S1 is my slack variable here. Then I'll have 6x1 minus 10x2 plus 16x3 plus S2 is equal to 36. So now I'm saying however much less than 36 it was, add the slack variable, and now it will be equal to 36. And then we'll have 3x1 minus 6x2 plus 9x3 plus S3 and have it equal to 6. Okay, so now for the positivity constraints, these right here, I'm not going to introduce slack variables for that because that's just a thing that has to be true. So this actually right here is 1 being satisfied. And while we're at it, we might as well check for 2 as well. Notice that each of these is indeed less than or equal to, 40 is positive, 36 is positive, 6 is positive. So less than or equal to 40, less than or equal to 36, less than or equal to 6. That right there is 2 being satisfied. Okay, back to the slack variables. So just to make sure that we understand this, let's go over here and say, let's say that, for example, x1 is equal to x2 is equal to x3 is equal to 1. Then I'll have -3 plus 8 minus 4 is equal to 1, right? So 1 is indeed less than or equal to 40. How much less than 40 is it? It's 39 less than 40. So this would tell me then that my slack variable, my S1, is equal to 39. It makes up that slack. So in other words, I would have -3 plus 8 minus 4 plus 39. And now suddenly this is equal to 40. So the slack variable makes up the slack between how much less than 40 it is, or how much less than. Okay, so our step 2 is to set up the initial simplex table, which really is like setting up an augmented matrix. What we have here is 3 equations where we have variables x1, x2, x3, s1, s2, s3, but we also have our objective function. And our objective function is also an equation. We're going to think of c as if it's a variable as well. So we'll notice the objective function is not of the form, all of the variables on one side with just the constant on the other. So when we're setting up the initial simplex table, the first thing that we want to do is move all variables to one side in the objective function. So what I'm going to have here is c minus 9x1 plus 16x2 plus 5x3 is equal to 0. Now, I'm going to take each of these equations, of which I now have 4, and I'm going to stick them in an augmented matrix. So I've already done that for us. So let's take a look at this augmented matrix. Notice the first row of my augmented matrix is the objective function. Now I've separated that from the other rows of the matrix with a line, just to make it easier to keep track of the material and what's happening inside the matrix. So my second equation, there is no c, so there's just a 0 there. Then I have -3, 8, -4. I have s1, so there's a 1 there. Then 0, 0, 40. So I've also separated my x's, my variables, my original variables, from my s's, my slack variables. Again, this is just to make it easier to keep track of the information in the matrix as we're applying row operations and doing things to try to cycle through those corner points. Okay, so my step 3 now is going to be to select the pivot. And this is going to be totally different than what you've done in the past for row reduction. This is not the same as Gauss-Jordan elimination. We're going to pick the pivot a little bit differently. So the first thing that I want to do is select the pivot column. And when I'm selecting the pivot column, I want to use any negative number in the C row, that is in the row that is associated with the objective function. So when I look at this, I only have one negative number there, that's -9. So that means this column right here is my pivot column. And now I want to pick my pivot row. Wait, actually, before we do that, so this was the only negative number in this one, but note that sometimes you might have more than one negative number up there. So how do you choose between them? It really doesn't matter. But if you pick the one, if you select the one that's furthest from 0, that will usually get you to your final goal fastest. So pick the negative number that's the furthest away from 0. Now, to pick the pivot row, we're going to do something a little weird. I'm going to take those constants and I'm going to divide each constant by the value from the pivot column. So I'm taking each positive, non-negative, non-zero entry, and I'm dividing it into the constant. So when I look at this, that -3, it's negative, so it doesn't matter to me. Negative numbers, I just put a little x, they're not important. 36, I will divide by 6 to get a 6, and 6, I will divide by 3 to get a 2. Now, in order to pick the pivot row, I want to take the smallest of these. The smallest determines the pivot. So here I take the smallest, which means that row 4 there is my pivot row, which makes this 3 a pivot. So totally different than what we did for Gauss-Jordan elimination. We've picked our pivot. Now what we do with that pivot is going to be quite similar. Okay, so step 4 is to perform row operations to create zeros both above and below your pivot. Now pivots of 1 are actually totally not necessary. We can do row operations to make zeros even if you have really gross numbers. If you want to make the pivot 1 though, I advise you to only do it by multiplying by the reciprocal. Don't try to add some value or subtract some value from another row. That's actually really dangerous when you're doing the simplex algorithm. So that said, this 3 that we have right here is actually a really good pivot since every single thing in that column is a multiple of 3. So we're just going to do row operations in the same way we would have done them before to create zeros. So I will do row 1 plus 3 times row 4. And here you want to be really careful. That line right there often can be a little bit confusing, making you think that the 3 that's our pivot is in row 3. It's row 4. Even though it's above a line, the objective function row is still counts as a row. So I'm doing row 1 plus 3 row 4, row 2 plus row 4, and row 3 minus 2 row 4. And that's going to make zeros in my pivot column. I'm also going to be changing everything else in all of the rows. So including the slack variables, including the constants, everything's going to be changing. Okay, so I've done my row operations, and this is what I end up with. I have zeros everywhere else in that column, and notice that the slack variables also changed, my constants changed, everything changed. So this brings us to our next step, step 5, which is to repeat steps 3 and 4 until there are no negative entries in the C row. So when I look at this, I do have a negative entry left over in the C row. So I'm going to repeat steps 3 and 4. So step 3 is to choose a pivot. Now I'm going to pick my pivot column to be the negative number that's the furthest away from 0. So that's that -2. And then I want to pick my pivot row. First, I need to eliminate any rows that have negatives or zeros. We're only looking at positive values. So that -6, not important. So then I'm doing 46 over 2, which gives me 23. And here I'm doing 24 over 2, which gives me 12. That 12 is the smallest, which means that 2 right there is going to be my pivot. So I'm putting a little diamond around it, that's my pivot. And I'm going to use it to make zeros everywhere else in the column. Now 2 is a good pivot because everything else is a multiple of 2. So that means I will do row 1 plus row 3, so my pivot's in row 3, row 2 minus row 3, and row 4 plus 3 row 3. And that's going to allow me to make zeros everywhere else in that column. Now, numbers in all of the other columns should also change, but I should not be getting rid of any zeros that I've already made. Everywhere else in that column is 0, and my pivot column is 0, so all of those are going to stay 0. Okay, so we end up with this matrix here, and first my pivot column was this, and then my second pivot column was this, and we want a line to separate that C. Now notice there are no negative numbers left in the objective row, which means I'm done. Done because there are no negative numbers left. Yay, which brings us to our step 6, which is to read the answer. And this is also a place where things change a lot from what you were doing before. So in order to find the feasible solution, in order to read these matrices, basically what we're going to do is every single variable that's in a column that doesn't have a pivot, we're going to assign it the value of 0. And every single variable in the pivot column will receive the value from the constant column. So I'm going to go back to this matrix right here, and we're going to see how we can read it from this step right here. So when I look at it, my pivot columns in this case, my columns that already have my pivots done, are the C column, the X1 column, but notice my slack variables also count. So my S1 column and my S2 column. So when I read this, each of those is going to take the value from the constant column. All of the other variables will be 0. So in other words, my C will be equal to 18. My X1 will equal to 6, except we have to divide that 6 by 3 because it's not a pivot of 1, it's a pivot of 3. So I'll have 3x1 is equal to 6. X2 doesn't have a pivot, so it's 0. X3 doesn't have a pivot, so it's 0. S1 does have a pivot, it's 46. S2 does have a pivot, it's 24. And S3 also is not a pivot, so it takes the value 0. So this right here is actually one of the corner points of the region. If we were to graph it, this would be one of the corner points, and the value that C would take at that corner point is 18. So in other words, we're saying C is 18 at the point, so not 6, but 6 divided by 3, so 2, 0, 0. And in the point, we're also going to include our slack variables. So that's 46, 24, 0. Okay, so that's not my final answer because I wasn't done yet. So let's go now and look at the final simplex table. And the variables that have pivots here are my C column. So C is a pivot. Now X1 and X2 are pivots, and S1 is also a pivot. So those variables will take on actual values, while every other variable will take on the value of 0. So here, this is saying C is equal to 42, 3x1 is equal to 78, 2x2 is equal to 24, x3 is 0 because it doesn't have a pivot, S1 is equal to 22, it did have a pivot, and S2 and S3 are both equal to 0 because they are not in pivot columns. So what that means is my final answer here is that C has a maximum of 42. Oops, let's do this in black. C has a maximum of 42. At the corner point, 78 divided by 3, so that's 26. 24 divided by 2, so that's 12. Then 0, then 22, 0, 0. And this right here is actually my final answer. So just to kind of go back to what we were thinking about in terms of graphical optimization, if I were to go back here and read this, this is like saying C equals 0. Actually, let's do that in green. This is like saying C equals 0. All of my original variables are also 0. So we're at that corner point 0, 0, 0, and at that point, the slack variables are literally making up all the difference. So S1 is 40, S2 is 36, and S3 is 6. Okay, so basically this is saying we started at the corner point 0, 0, 0, then we moved to 2, 0, 0. Then we moved to 26, 12, 0. And it turns out that that's the corner point that maximizes this. And the reason I can see that is because there are no negative numbers left in my objective function row. If I had a negative number yet left, then I would have a chance of making that even bigger up there by adding something from my pivot row. But there's not, so any row operation I do from now will actually cause that 42 to get smaller. So we kind of have found our maximum value. And this right here is the simplex method. So in class, we're going to do some word problems to understand the importance of the slack variables. And if there are any minor questions that you guys have, like for example, what happens when both of these numbers right here are the same? That type of thing, we'll do a couple examples in class to try to answer any questions that you have. Also, we'll see how to minimize. That's it for now. Bye guys.